Okay, so kind of wrapping up our discussion of gas laws, I do want to introduce kind of one additional concept here. And I want to make very clear there are some equations we're going to talk about here. I don't consider these equations particularly useful equations for doing calculations with. So a couple of the equations we'll see on the next page will not appear directly in any problems that we have on the exams. I think the main idea here of the kinetic molecular theory is to give you a framework to relate what's happening on an atomic or molecular scale to what is happening on a macro scale for a gas. So the idea here would be to maybe get an understanding of why, say, temperature and pressure are related by thinking about how the molecules are interacting with the container that they're in. So a good example of kind of applying kinetic molecular theory, which I'll talk about in just a minute, might be a car tire, right? So the tire pretty closely has a fixed volume, but the pressure in the tire is related to how much gas is present or what the temperature is. So it's not uncommon, particularly as we kind of move into the fall, if this is a fall semester class, temperature starts to go down, you may need to put a little more air in your tires because the pressure goes down, right? So in that case, you increase the number of moles and the pressure goes up. But before you put in that extra gas, right, the pressure in your tire went down as a result of the lower temperatures outside. If we think about just the molecules of the gas moving around, right, how fast a molecule in the gas phase moves is directly related to the temperature. So when the temperature is higher, the gas molecules are moving more quickly. They're more likely to collide with the walls of the tire. That's what generates the pressure, are those collisions between the moving molecules and the walls. As the temperature goes down, the molecules aren't moving quite as fast. The collisions with the wall of the tire are not quite as frequent. That can cause a lowering of the pressure in the tire, right? And since we can't really change the outside temperature as winter sets in, we add a little more gas to the tire. So that's kind of the idea of the kinetic molecular theory. We want to be able to make some connections here. So a lot of this, I'm just going to be reading off what I have on the lecture notes. So if you don't have a copy of the lecture notes, that might be helpful here. Because I do want you to have a general idea about some of these issues, but again, there won't be really calculations that we're doing here. So kinetic molecular theory, let me see, I've got the sun just kicked up and it made some differences in the shadows here. So let's see if I can adjust that a little bit. Okay, a couple of main points to the kinetic molecular theory here. Gases consist of large numbers of molecules that are in continuous random motion. The combined volume of the molecules of the gas is negligible relative to the total volume. Attractive and repulsive forces between gas molecules are negligible. Energy can be transferred between molecules during collisions, but the average kinetic energy of the molecules does not change with time as long as the temperature of the gas remains constant. So energy directly related to what the temperature is. The average kinetic energy of the molecules is proportional to the absolute temperature. Okay? So for a lot of this, we can relate how the gas molecules are moving to the temperature, right? And then we can derive things like pressure or volume from how those gas molecules are interacting with the walls of their container. Okay? Now, a couple of ways we can apply some of these ideas are here on the next page. So if we think about gases moving, and it could be through other gases or it could be through openings where there's no other gases. These processes are called molecular effusion and molecular diffusion. And I actually have these kind of strict definitions here to go over. Effusion is when there's a barrier with one or many small holes that prevent a gas from expanding into the new volume unless a gas molecule happens to travel through a hole. And diffusion occurs when the holes in the barrier are larger than the mean free path of the gas. If there is no barrier at all, you can think of a barrier with one large hole big enough to cover the boundary between the two volumes. this would mean the gas will diffuse into the new container. So this is essentially what happens when you open up pressurized gas. If you think of opening something like a bottle of soda, there's carbon dioxide in there. When you open the soda, psh, that's the gas expanding out into the new volume. That's diffusion. That CO2 coming from the soda bottle is going to diffuse through the gas nearby. Effusion is more like gas escaping from a balloon. So if you've ever had a helium balloon, when you bring it home, it floats, right? It might go right up to the ceiling, but overnight, the helium molecule atoms that are in there can escape through the material of the balloon. So there's tiny holes in the latex. Those atoms of helium are pretty small, so they're moving with pretty good kinetic energy, and they're likely to escape through the walls. So your balloon doesn't stay afloat. Eventually, the more the helium escapes, some of the air that's in there stays in there, right? And by the next morning, your balloon may be kind of down at eye level, or eventually it's going to fall down to the ground, because those larger air molecules like the oxygen and the nitrogen are not going to escape as easily through the holes. They're not going to effuse through the walls. Okay, so two equations here that I want us to think about, and I really would like you to have just a general idea of some of the relationships here. So one here is called the root mean square speed. So this is related to how fast the gas molecules are moving. This is abbreviated with a U here. So the root mean square speed is equal to the square root of 3RT, so that's the gas constant and the absolute temperature, divided by mm, as I have here for the molar mass of the gas. So two relationships here that are worth thinking about. The speed is going to be directly related to the temperature. So the higher the temperature, right, since temperature is on top of the fraction we have here on the right, the temperature goes up, the speed of any gas is going to be higher. Temperature goes down, the speed of the gas is going to be lower. The other relationship would be molar mass. Molar mass is on the bottom of the fraction here on the right side of this equation. So if the molar mass goes up, we're dividing by a bigger number, the speed is going to go down. Molar mass goes down, dividing by a smaller number, the speed is going to go up. So at the same temperature, molecules with larger molar masses will move more slowly than molecules with lower molar masses. So direct relationship between temperature and speed, inverse relationship between molar mass and speed. So we could compare one molecule at different temperatures, or we could compare different molecules at the same temperature if we know their formula and can figure out their molar mass. Okay. This leads to another equation here called Graham's law of effusion. This, of course, would work for diffusion as well without a barrier, just gases moving with each other. We can compare the rates of two gases effusing to the molar masses of the gases. So the rate of gas 1 relative to the rate of gas 2 is equal to the square root of the inverted ratio of their molar masses. So we've got 2 on top here, 1 on the bottom, and there's a square root relationship here, just like there is back up here for the speed. So we can compare, right, if two gases are spreading into the same room, for instance, we can compare their rates by just comparing their molar masses. Okay? There's actually a kind of nice experiment where you put you can put ammonia, like soak ammonia in a cotton ball, put it on one end of a glass tube, soak some HCl or hydrochloric acid in a cotton ball, put it in the other tube, right? And then you'll actually see ammonium chloride solid form where the two gases meet. And as the gas is effusing, it would actually be diffusing in that situation, is diffusing down the tube, you can kind of do a calculation to predict where it would be that the gases should meet, because ammonia, NH3, weighs about 17 grams per mole. It actually diffuses a lot faster than HCl, which is about 35.4 plus 1, 35.5 grams per mole. So it's actually quite a bit closer to the side where you put the HCl, where you'll actually see the solid form. Okay. So one other thing I want to talk about, most of this chapter we've talked about the ideal gas law and using ideal gases for calculations. And it turns out you can't always just make the assumption that gases are going to behave ideally, particularly if you get into industrial job, a chemistry job, or if you get into something like chemical engineering, you often have to factor in the real properties of gases. So there are two particular assumptions that the ideal gas law makes. These were mentioned in the description of the kinetic molecular theory. But if either of these becomes relevant, we can't use the ideal gas law. So the two assumptions for the ideal gas law is that there's no molecular volume. So we don't worry about how much space is occupied by the atoms or molecules themselves, just how much space is occupied by the gas. That's pretty good at low pressures where the gas is really spread out, but at much higher pressures, like you might have in a reactor at a chemical plant, pressure gets really high, the molecules are actually pretty close together, even though it's still a gas, and the volume of the molecules themselves may be an important factor. So the ideal gas law might not hold anymore. The other component or assumption in the ideal gas law is that there are no interactions between the molecules. Now it turns out, depending on molecular structure, there can actually be fairly strong attractions between different molecules. If that's the case, the molecules are actually being pulled towards each other. That's going to change the behavior of the gas. So depending on the structure of the molecule, which is something we'll talk about in a couple chapters, we may have to worry about intermolecular interactions between molecules in the gas. Now, if we do need to factor these in, there is an equation that kind of eliminates both of those assumptions. It's called the Waals equation. So this is also something you could do a calculation on, but I think this is a little beyond what we should be focusing on in this chapter. There are two variables here in the Waals equation, just labeled A and B, that account for these two observations. So what we do, and you could look these up in a table if you needed to do this calculation, right? So this is a form of PV equals nRT. The pressure, though, is being adapted by this variable A to account for the intermolecular interactions of the gas. So if the gases are attracted to each other, they may be making a little bit less pressure. If they're repelled a little more by each other, they may be making a little more pressure. We can also adjust the volume of the gas by how much space the gas might be occupying. So there's another variable here, B, that we can plug in along with how many moles of gas to maybe make an adjustment on the volume. So if we're looking at a real gas, right, maybe it's high pressure, maybe it's a gas that has particularly strong intermolecular attractions, we could use the Waals equation here to solve maybe for, right, what temperature should we be doing this reaction at, or what is the pressure actually going to be in the reactor that we're looking at. Okay, that's the end of chapter 6. So stay tuned for a practice test because we're ready for our second exam now.